Skif Sokolov, is he here?
Yes.
Let us start panel discussions. I would like first to ask participants of this panel to come to the table. Mitra Abkhaz from BABA, then Astrophysical Institute, Professor Sokolov Vladimir, Professor Stefan Kosar from Alpha Institute, also Professor Alexander Sakharov. Now the change atmosphere to a little more friendly and relaxed, and say that we should be express first gratitude for the organizing committee, so gave the possibility to such an industry discussion, and gratitude to the concept of black hole, which helped much to draw public attention to astrophysical research and boost it technically, ideologically in all directions. And so the astronomers have a large task what to find on our large sky, and reasons why one must improve accuracy hundreds and thousands of times to see something. Questions concerning black holes, but it is not rigid limitation. There are some other questions that can also maybe touched if they are relevant to the subject. One can also express his own personal views, which not always can be supported by the rigorous proof of this viewpoint, but may reflect the aspirations of persons, so the predictions what may happen in the future with this theory. Nowadays, there are very serious accumulation of experimental evidence for existence of very heavy and compact objects. Alexander Sakharov.
First question about definite observational or experimental proof of existence of black hole. First, of course, we have to find definition. What is proof? It's not only for black hole concept, but for other concepts in physics. It's about, for me, it's clear that this model, this concept is working. But of course, it may be not final concept for this observational data. It's like, for instance, for concepts in atomic or particle physics. Initial for ancient Greeks, atom was some single unit. After that, people recognize there are particles. Particles have quarks, etc., etc. But it's just for my view concerning proof, for instance, people are saying there is no proof for event horizon. Okay, but at the moment, for me, there is a confirmation that is until the last unstable orbit for black hole at the galactic center, we have confirmation of general relativity prediction. At least alternative theory has to explain the same observational data at least until this level. Second thing, it's concerning theoretical problems with black holes. It's, of course, there are some singularities. Some components of Riemann tensor may be infinite. Of course, it's from theoretical point of view, it's not very pleasant situation. But again, it's a disadvantage. But advantage that model is very simple. Again, it's like Wheeler inside. people know that is we need infinite time for collapse to get a black hole as a result of stellar collapse. But
Infinite time
yes.
Outside observer.
yes, for distant observer. But again, but black hole as a limit is much more simple than collapsing stars. Let us try to use the limit, take into account the differences are almost negligible. And third question. So, we have to keep in mind that not only, we observed, as Cherepashuk mentioned, we observed black holes with stellar mass in binary systems. We observed black holes in the galactic center. People are speculating about black holes in the intermediate masses, with masses about 1,000 masses. But we have to keep in mind that our observational or experimental facilities are limited. So in this case, probably, again, there are problems how to detect single black hole with stellar masses. Probably it's because in this case we have to observe some aggression onto this object, but initially probably microlensing could give some hints about this existence of this kind of objects. But concerning primordial black holes, with the model, it's possible, but we take into account observational constraints, we have no need to introduce primordial black holes. That's it for the beginning.
When we are saying about the black holes for theoretics and for observational people, for observers, the theoretics say about singularity. Yes, the singularity of what? Singularity for densities, first singularities, and the second singularity for force, gravitational force, near the gravitational radius. And if we have the black hole candidates near with the solar mass, like in the X-ray binaries and so on, we have solar mass candidates, and maybe we have huge densities, maybe infinity densities. The people don't know exactly what the answer for these questions. But for first, near the redshift, near the gravitational area, we have exactly from general relativity, exactly infinity force. Yes? And if we have the huge black hole candidates like ULAC, with 10 to the 9 mass of cells, we have the smaller and smaller densities. Maybe we are sitting near the under the horizon, because with a huge Schwarzschild radius. So we have for stellar mass density, we maybe have density infinity or not. But for 10 to the 9 and more density solar masses in the galaxy center and so on, we have smaller and smaller density plus forces near the redshift, near the horizon, always infinity. So we have two infinity for this theory. First and second, but for black hole candidates in the double systems, we have only observations, questions for this and so on.
There is indeed definitive observational and experimental proof of existence of black hole candidates, very massive compact objects. And this question must be addressed. And there are prima facie reasons, the way science has developed, to believe them they are black holes. The problem is very subtle. As I showed, Einstein did not believe. But he could not also suggest what's the alternative. Dirac, who is considered one of the finest physicists, he did not believe. But problem is so subtle that even he could not pinpoint where is the resolution. So ordinary astrophysicists, there is good reason apparently to believe that these massive compact objects are black holes. And I also, in say up to 94, even 96, believed that these objects are only black holes. It is only then some later thinking started that I found they cannot be exact black holes. They must be quasi-black holes. And in view of my proof in Journal Mathematical Physics, that such Massenpunkt, neutral point mass at exact m is equal to 0, these so-called black hole candidates cannot be true black holes. They must be something else. And this problem we all must address. So Stephens said that he does not believe in black holes, but he never addressed then what are these massive candidates. He should address those things also. He just cannot sit in black suit and black tie and deny black holes. So black holes problem is genuine. Apparently there is reason to believe, but this problem is very subtle, which me and some of my American colleagues have found, but it has not been very widespread. People do not know about the resolution. Resolution is that for if you take sun, finite, Schwarzschild solution is very nice, exterior. Then you have Kepler's law, very fine. But if when it goes to the limit of the point mass, it shrinks to the point mass, then this integration constant that time is 0. This a very subtle concept which I realized few years back, and my other colleagues, I have not been able to convey this to my other colleagues, so they still insist that these black hole candidates must be black holes. And we have reasons. There are many experimental proofs. There are intrinsic magnetic fields like much stronger than Newton's star, and these are something else which we have called magnetospheric eternally collapsing objects. They are quasi-black holes. For all purposes, their radius is same as black holes. The same K alpha line will be seen. The same thing even if you do imaging. Imaging cannot produce. He gave a very important point that these pictures of black holes is wrong. Actually, imaging goes only up to the photon sphere. You have a light illuminated sphere, you see. And for also black hole candidates, also you have you never see complete black because of strong gravitational lensing. You can go only up to the photon sphere. So experimentally, it is very difficult to distinguish, except for the magnetic field.
So it is dark hole.
It is dark hole. Dark hole from a distant observer, but locally strong magnetic field, and you see a lot of flaring and pulsar light activity. And the other question, there are lots of theoretical problems which I have described. That acceleration scalar, it is a scalar, it actually goes to infinity near event horizon, so which means it's a physical singularity. I pointed out a Riemann scalar, pointed out he's become infinity, that means it's a physical singularity. And this coordinate transformation, Jacobian becomes singular, that means you cannot say that you have remove this singularity by coordinate transformation. Then Jacobian should have been finite. They all go up at the event horizon. And the third question, the mass gap, I have told that mostly whatever black hole candidates, whatever they are produced out of gravitational collapse. Normally we do not have, because of radiation pressure, we do not have stars more massive than 40-50 solar mass. The massive star is Eta Carinae, around 100 solar mass, in fact which is going to give a gamma ray burst any time. So if 100 solar mass stars also collapses, it may produce a black hole of 40 solar mass. That is why gap. Then you have on galactic scale, you have collapse, then you have much more massive black hole candidates. And about the last question, whether the black holes primordial, so I think there is a question of there is no black holes, neither any primordial black holes, and this I will discuss in my afternoon talk. Thank you.
Stefan, whether the faults of general relativity described to us certain implications on the experimental facts, which were discussed by other participants.
Sure. There's no doubt that observations have shown that there are compact, dense objects. The question is, what are they? And people jump to the conclusion that it's a black hole, simply because they're getting used to now of the term black hole and talking about black holes without examining what the whole thing is. Let's ask ourselves, when we talk about black holes, what black hole are we talking about? Are we talking about the so-called Schwarzschild black hole, the Kerr black hole, the Kerr-Newman black hole, the Reisner-Nordstrom black hole? We need some more specification as to what it is. Well, those four black holes, of course, are one-mass universes. Let's consider, they're one-mass universes, and they can't be superposed, so you can't get multiple of those black holes. If we throw away asymptotic flatness, then all of those solutions can be discarded entirely in one step, because we can substitute certain mathematical relations that make it so. So I'm not disputing that there is observational evidence for these sorts of, for dark, compact bodies, but I'm disputing that they're black holes. Certainly those four types that I've listed have no basis. Now, are there theoretical problems with black holes? Certainly. Many of the things that I've argued there. Those black holes that I've referred to, they are defined in that way, and so they're in conflict with black hole with Big Bang models. These particular black holes are static, and they're not in the universe they're in is not expanding, and those ones that I've talked about are asymptotically flat. But the Big Bang models, they're non-static, and they are expanding, and it's not an asymptotically flat universe. So fundamentally, these two can't be put together. Superposition doesn't hold. You can't take that solution and stick it to another one. So there are major problems with the theory. Are there any outstanding mass between supermassive black holes and centers of galaxies, spiral galaxies and star-range black holes, etc.? Well, if a black hole is in the middle of a galaxy, it's surrounded by a lot of matter. But that violates the definition of the things that we're talking about. See? And it violates Big Bang models in that the Big Bang model is treated as a perfect fluid. But then galaxies are introduced arbitrarily. and so now we have a multi-body problem, or a multi-body solution, out of what started out as a single mass problem. There's no justification for that kind of idea. So black holes in spiral galaxies, again, what kind of black holes? Well, we see that these sorts of things don't have a basis in the theory that's consistent. Now, do we need to get primordial black holes? Well, there are no such things as black holes, so the primordial aspect of it doesn't hold. And then the Big Bang model, of where the universe comes into existence from nothing, according to many proponents of this idea, but it's a perfect fluid model. So you don't have multiple bodies. There are no solutions to Einstein's field equations. There's no for more than two bodies, and there's no existence theory. If you want to apply numerical methods, first demonstrate that you have a well-posed problem by providing an existence theory, something like this. Otherwise, it's all just guesswork. That's about all I'd like to say on those four questions.
As I have heard everybody, so most people, most participants and other people discuss some simple analytic solution and do not mention the possibility of numerical study of binary stars, of galaxies, which may give more insight sometimes on all these questions, because concentrate on some simple solutions which were take 100 years ago doesn't move as much further. There are much more details in all this. So probably it is more interesting to discuss dynamic, whether one can prepare something like that, whether there can be conditions in which something like that may occur. So, pure theoretical, you can invent different spaces, different topologies, so they are not able to make them physically. So, my slogan is closer to physics.
Okay, but I would like to respond.
Yes,
But it's in some sense, I think it's, it's some discussion. It's not, it's a little bit biased because it's three people express their skepticism, but I'm like optimist in minority. But it's, I would like first, last speaker, last panelist, he mentioned that there are some disadvantage faults or some minor issues in general relativity. I dislike this theory because but it's like to say, okay, I dislike this world because it's not perfect. Really, it's not perfect, but there are some problems, but as elsewhere. As majority of audience are people working in atomic and nuclear physics. So assume that Bohr invented his model for atom. That's it. We could say, okay, we dislike this model because there are many inconsistencies. But we do not use it. Okay, go ahead. But you have nothing. Probably we have the same position now in black hole physics. So its model is working. If you are criticizing, okay, please suggest some other thing. Next issue. It's in some sense, I think there is some methodological misleading, especially in black hole concept. All this we are considering in physics and nature in general, we are considering models, only models. And elsewhere, in models, we are saying, we are reporting, for instance, to our authority, we are saying, we are really investigated nature. Of course, we investigated models. And also we investigated concept or model. Always we have candidates. Even for particles, we have candidates. Of course, with different confidence level.
Even for academic students, we have candidates.
Who? No. I'm freelance. But it's some misleading. But of course there is natural skepticism started since Einstein times because there is singularity. But at the moment, suggest other models. That is constructive approach.
Vladimir Sokolov, to answer this question, why the gap of missing masses of stars, there is certain range of masses where no stars at all exist, at least observed in the universe, is so important.
It is very interesting question because now we have some possibility. Now the black holes is the main proof for black holes is a mass under gravitational compact object. So we must have about the some compact objects. In X-ray binaries and in center of our galaxy and maybe so. But Sasha are going to prove that to see what is it under horizon. I think. I think. But for us for observation also for X-ray binaries, we have instead of the mass, we have some possibility to see what the original for before the black holes. So I must gamma bursts and so on and so on.
What are parents of them?
Yes. What are parents of the GMEs of black holes? But now black holes only believe, I think.
Yeah.
Because if we don't like to say black holes instead of candidates of the black hole, we haven't money to observe.
I agree with Alexander that general relativity, despite some conceptual problems, is the best theory. It is the best paradigm to explain things. And much of the problems Stephens mentioned, I do not agree with them. Energy momentum, the field energy has to be a pseudo-tensor, because in a free-falling frame it must vanish. And there is no problem with conservation, so it is the best theory. I also agree with the comment of Alexander that it is not enough to say that black holes are not there, something, there must be constructive criticism. This is very important, and we must address these points. What are these massive compact objects? So this is what I would say in the last 5 years, me and my colleagues have indeed addressed. This radiation pressure, when something concept is the Eddington luminosity, you can have compact objects. I told it, Hoyle and Fowler did it first in Nature paper and Monthly Notices paper in 1960. Even in the paradigm of Newtonian gravity, if the radiation pressure is so high, the Eddington luminosity observed, you have quasi-static objects. They are called supermassive stars. They are described in Shapiro-Tucholsky's book, also famous Weinberg's gravitation book. And what we have shown that when you incorporate general relativity, you can have extremely relativistic radiation pressure supported stars, which they are always trying to approach the exact black hole solutions. We believe the Schwarzschild solution is correct, and it is approaching that static solution. These are quasi-static solutions, what we are telling, and it is approaching. As it approaches, it emits radiation, and the constant mass is diminishes, it goes to zero to the exact solution. This is the constructive solution. These are hot balls of plasma with strong intrinsic magnetic field, and they have vulnerable to eruptions like solar flare kind of thing. So this is the constructive solution, and there are evidences. My American colleagues have published several papers that in quasars, X-ray binaries, in the same neutrons that have intrinsic magnetic field, and this echoes have intrinsic magnetic in the same paradigm. Many of the things can be explained. So these are developed through several papers. It could not be done much because we do not have students. And one of those things, Daryl later, he actually expired in 2011 also. And if whether the black hole concept is established or not, people understand. I can narrate an episode if the chairman would permit me, that actually people know that it is correct. I can narrate a story if you admit. Can I narrate?
Questions which were not answered during the presentations of reports because of lack of time, but now it is possible to ask questions to all the participants of the panel.
The first question of this list, and it's written about observational, but not only observational, but also experimental proof. To my knowledge, there exist only 2 experimental papers devoted to the research of micro black holes, publications made by the CMS collaboration at the LHC. Both, the conclusion of both papers were negative, and just some limits for the mass of supposed black holes were implied from these papers. What's your opinion? I just ask all the panelists. What's your opinion? What is the reason for this failure?
There are a lot of media hype and hoopla that LHC will find black holes and maybe universe will be destroyed. So this was based on one interpretation of string theory. Now we expect the quantum gravity to take over at 10⁻⁹ GeV scale, but then string theories are constantly changing their stances, and they want some observations should come out and come from string theory. So this was one of the prediction of one variety of string theories which said black holes should be there. Again, this is what they mean, that even at TeV scale, the quantum gravity would operate, even at a very microscopic scale, what they really mean that gravitational pull-ups would take place. And that they say by black holes, because the particle physics do not discuss all these details, intricacies and subtleties of the problem. They mean that gravity would take over, whatever strong forces, other forces, so gravitational pull-ups would take place and something would be formed. In any case, no such signature has been found, probably even in black hole formation. That was a big news. LHC, no micro black holes is found. And in our opinion, that whatever, even if collapse will take place, it will become hotter and hotter. And again, the same Eddington luminosity would work. And you may have a hot ball of microplasma, which you might interpret as black hole if you wish, but it is actually not black hole. And what this shows, the string theory prediction was wrong. The TeV scale gravity would take over quantum gravity.
Actually, I'd like to criticize the first question in general. I think it's not the scientific questions at all. Saying for example, in Higgs search, the question would sound like, is there a definite observation experimental proof of the existence of the Higgs boson?
Right.
Yeah. And this is absolutely a wrong question. What the right question is, what are the observations of object with properties like Higgs boson? And this is what we are doing.
How much
Right.
is consistent?
Which is behind that black hole. Well, so as far as I know, the observables are consistent with classic black holes.
Probability.
Yeah. And now I'd like to remind you about the duck test. You know what it is. So if it looks like a duck swing like a duck and walk like a duck, then it was likely a duck. Yeah, and so I guess we're in this situation, and I'm very disappointed that those two talks about criticism of generic theory was not accompanied by any experimental observables which would distinguish that one from another. Without that experimental observables, I guess it's arguing about terminology, nothing more. It's not a science.
Absolutely.
That it is the intrinsic magnetic field, so-called black hole candidates will have strong intrinsic magnetic field. This is, I repeatedly told you and answered you. You did not listen. Black hole candidates will have strong intrinsic magnetic field. They will be vulnerable to radiative disruptions, which is seen. An intrinsic magnetic field has been inferred strong magnetic field both for X-ray binaries and at the quasar level, which was University press release in 2006. So we made this prediction. Also, we made this, and I answered you also before.
So this person asked you how to distinguish black hole plus external magnetic field, intrinsic. But it's probably it has to be some more definite signature. You have to find more definite signature, like some spectral.
Yeah, that signature is the neutron star. When you have strong intrinsic magnetic field in a binary, you have propeller action. Two things act there: neutron star spin and accretion disk spin. And magnetic field couples with the inner accretion disk. Then something can happen called propeller action. This is a definitive prediction. And what Robertson and later showed in their first paper and series of papers, that in these cases, so-called black hole X-ray binaries, you have this kind of propeller action. By that they explained in a common framework. This has been done in this series of papers, Astrophysical Journal later, Monthly Notices Royal Astronomical Society.
Pointing plots or whatever to distinguish that observables inside your presentation, not as an external reference. It is because it is a key point. Without that those statements make a little sense to me as experimentalist.
If we have a surface for black hole candidates or not surface, if we have magnetic field, like or maybe we must think about surface of this object, and we must think about the surface about black hole candidates in solar mass. It's first observational task for us.
Speaker also spoke. He has spoken, and I have tried.
You are not that about such.
And this is very important point, and this is really addressed, that what we have tried to show in Monthly Notices Royal Astronomy 2010 paper, me and Glendinning from Berkeley Research Lab, that this stellar mass black hole candidates are balls of plasma, and all black holes have balls of plasma. So they do not have a hard surface. So you do not have type 1 X-ray bursts. Then there is another point which was raised maybe by him, and maybe the first speaker, that pulsars have regular pulsation periods, very well defined. And this is a very important question. Why black holes you do not see such kind of spin period? These also in one of the preprints we have explained that there is very strong this thing called lens thinning effect near black holes because of strong gravity. So time reference changes. So signal, even a periodic signal starts, it gets distorted in the very strong gravitational field, and so periodic signal becomes diffused. That is the reason we do not see definite period from black hole candidates. Both these questions have been addressed.
It's about neutron stars. In principle, there is opportunity to find surface, but if we do not see surface, we could not claim for sure that we have black hole. So because it's not, I mean, like doctor, it's after examination, okay, no viruses, but I mean, it's not they do not observe viruses, but it may be special, you know. It's the same situation. So, concerning question about existence, you know, I would like to remind you that, for instance, for the galactic center, 30 years ago, there were many models, including fermion balls, bosonic stars for galactic center, and black hole, of course, like one of the simplest. But size of this object was greater than trajectory of stars. In this case, okay, simply choosing, I mean, suitable model from these three models from the market, okay, people are right, but it does not mean that it's final model. It's not the best. But at the moment, people do not suggest, probably they are not smart enough to suggest some better model, but that's it.
One more problem in the list. Having dark matter, we should have black holes consisting of dark matter. So my question is, there are some theoretical models for such objects. My question is, are anything observed from the observational point of view, something which may be interpreted like this, anything rotating around nothing and behaving like the black hole consisting of no matter?
Another type of black hole.
No, maybe there are
another nature,
some
not made
observations
of hadrons.
of such a particular exotic objects.
Okay, but let's could I tell something? But I do not understand the answer. But I could start to. I do not understand the question, but I could start to answer. But it's but it's, you know, it's typically people observed also gamma from the galactic center. Astroparticle physicists are saying, since there is a gamma, probably there is neutralino annihilation. It means dark matter concentration. This conventional model, there is some concentration of dark matter. I mean, some conventional, let us say. But in principle, trajectory measuring of gravitational potential of these bright stars and, I mean, with measuring of size of shape of shadow could give information about potential. If you know information about potential, we could clarify model. Is it model only black hole metric or plus something? We could understand it.
No. Any candidates on black holes which have different predictions from those given by the Schwarzschild model, say?
Yes, people consider the other opportunities.
Not people, other experimental evidence for this.
No, experimentalists are saying only about experimental.
Do they see this or not? Question is.
No.
This is a simple answer. No. I ask this. You said you don't understand the question. You understand, but no, give the answer.
I just wish to point out various things which are held as standard views among general relativists and in fact more generally among geometers and other people. There's nothing wrong with a Jacobian for a transformation being infinite or zero in various places. This happens all the time in free space, if you consider spherical polar coordinates at the pole or something. So there's nothing wrong with it at all. It's not saying there's anything wrong with the metric there. It's entirely saying there's something wrong with a particular coordinate system, so then you need to choose another coordinate patch. They were overemphasizing there was something wrong with the metric rather than there's something wrong with a particular coordinate system being used.
Jacobian could be infinity singular, but that is at the origin of the center. r is equal to 0, not anywhere else. If it is occurring anywhere else, then this signifies a problem. If in a transformation you have to equation g prime is equal to j square g, so then it is a rule that or meaningful this must be non-singular. You must check, this is written in a mathematics book on curvilinear coordinate transformation. It is assumed that Jacobian is non-singular.
That particular point. If one of the charts happens not to be valid, then it is also a symptom that the Jacobian between the two charts will itself be singular. So you'll get both the things. You'll have
This
the
matter
Jacobian
that you
going
raised-
bad and the Jacobian going bad as well. That's perfectly okay because there's another coordinate system that you can move to in which the coordinates behave perfectly well. For instance, in this case, the Euclidean coordinates are in free space. They work everywhere.
Saying in my talk, because I didn't talk about coordinate transformations at all. I talked about the Hilbert metric and the insertion of Newton's expression for escape velocity, which is an implicit two-body relation in what's alleged to be a one-body problem. I didn't say anything about coordinate transformations, so that's got nothing to do with it.
That applies to his talk. But for this particular point here, firstly, it's a coincidence that escape velocity is the same in Schwarzschild and in Newtonian theory. If you do it for more general black holes, the two do not always coincide. The usual argument has to do with the mass as perceived by an observer far away, setting a value of a particular constant for that solution.
This can't be so because the solution that you're talking to relates to a space-time that by mathematical construction contains no matter.
It's perfectly okay for it to contain test masses for the purpose of describing things like escape velocity or motion of particles far away.
That's not so because in two cases we're told that the escape velocity is c from the event horizon, but we are also told that nothing can leave. This is a contradiction that I pointed out.
It's perfectly normal to say you have...
So you cannot have a normality with an escape velocity of c and nothing can leave. So that this is a contradiction. So no matter which way you turn it, it's still a contradiction. You cannot have an escape velocity and not have an escape velocity at one and the same time. That's the point I was making. You didn't seem to follow that too well, but that's what I'm making the point of. So the whole idea of escape velocity in this instance is just a play on the words escape velocity, as McVitie pointed out in 1978.
Probably we will not conclude do black holes exist or not.
My own microphone. So, as we have seen, the problem is acute. The research is going rather fast in this area. And there are certainly new problems which arrive, which is much stressed that for some reason black holes are no stars creates within certain intervals of presence. So we can explain this. If there is a mass of gas that could be in this range, somehow it cannot collapse. It can collapse, but not to black hole. There's some other new phenomena that something is impossible. Yeah. And I would like to stress another thing which is important. That everybody, of course, uses models. But the efficiency to use models very much depends on our knowledge of the equation of states of matter. What happens when gas is very much contracted? Does it become quark-gluon plasma? Or does it become some other matter with different dependence of pressure, of temperature? Does it remain unstable or becomes unstable and goes to explosions? You know that stars explode, and that also is related to black holes. So, but to make the models and to compute what really will happen with the masses of matter, with gas or maybe gas with dust. We need more knowledge for elementary particle physics. Then it will provide more tools to distinguish between different types of objects which we see in the sky. So thank you very much.